pleasure to introduce James Hongyi Zeng. We know him as James, but as we know, that's not his real name. He's been with us since 2008. I first met James because he came and presented to me a design for a radio addition to the NetFPGA board. And he came in, I didn't even know he was doing it, did this entirely on his own, just showed up in my office and then demonstrated the system working. And so I immediately invited him into the group, expecting that he would spend the next few years designing hardware. And he had better ideas and better plans, and ended up working to start with payment on network verification, and then branched out on his own into this work on data plane testing and dynamic testing of data planes. So I'll let him tell you the details, but pleasure to have you here today.
Thank you, Nick. Good morning, everyone. My name is James Zeng. Today I'm going to present the automatic data plane test. So this was one email I got from our network admin last year. It said that between 6:20 p.m. to 7 p.m. tonight, we experienced a complete network outage in the building when a loop was accidentally created by stubs. We are investigating the exact circumstances to understand why this caused a problem, since automatic protections are supposed to be in place to prevent this from happening. So this was just one instance of a network going down. The web is filled with all kinds of service outages. Nowadays, networking are reaching the utility status, expected to run 24/7. When they go down, the effects are catastrophic. So why debugging network is so hard? First of all, modern networks are very complex. There's complex interaction between multiple protocols on the same switch, and there's a complex interaction between state on different switches. And the result is that there are multiple uncoordinated writers to the state simultaneously. And as a result, operators cannot observe all the state because they are distributed, and they cannot control all the states because they are controlled by the distributed protocol. But most importantly, debugging is so difficult because of the lack of the automatic testing tools. So the battle of the troubleshooting becomes, on one side, there are various sources of hardware problems such as buffer overflow, fiber cards, broken interfaces, misstable cables, and flaky links. And there are software problems such as firmware bugs and crash modules. On the other side of this battle, we only have a small set of rudimentary tools like ping and traceroute, plus network engineers' wisdom and intuition. So before I describe how we help network engineers to win this battle, let me first clarify the focus of this talk. This talk is about data plane testing. So what do I mean by that? So first of all, you have this network. It's just some switches interconnected together. Then within each switch, you have this forwarding rules that determines the packet flow. An example of forwarding rules would be something like, for example, in the L2 switch, it's something like if destination MAC address equals to X, then forward the package to port 1. But in general, these kind of forwarding rules are just match plus action tuple. And on top of these forwarding rules or forwarding tables is the control logic. The control logic is the what we call the routing protocols that rise to these forwarding rules. For example, like BGP and OSPF. And in this talk, I'm not interested in the control logic correctness. In other words, we are not interested in the routing protocol correctness. Instead, we will focus on the forwarding rule, the data plane. So what do I mean by data plane? There are two main goals to verify data plane. First, we want to verify the forwarding rules correctness given the topology and policy. And topology is easy to understand, just how the networks are connected together. A policy is something like the front-end web server cannot talk to the back-end database directly. And the other goal is to verify the network performance given the service level agreement. A service level agreement is a contract between the network service provider and its users. An example agreement would be something like from point A to point B, the latency should be no longer than 5 milliseconds. Why do we care about the data plane testing? There are three main reasons. First of all, the network problems must have some data plane effects. Otherwise, it's not a user visible problem, and why do we care about that? And secondly, focusing on the data plane testing helps us to trace back to the control logic problem. And finally, there are some certain kinds of the problems, such as performance and hardware failures, that cannot be detected by the control logic viewpoints. They can only be detected by data plane testing. So what would automatic data plane tester look like? First, you have a network, right? And all the data plane information, such as the forwarding rules and topology, are collected through these automatic testers. And in some cases, these informations are enough for the automatic tester to reach its conclusion. But in other cases, automatic testers may choose to send more test packets based on the information it collects from the data plane. And then these test packets will exercise the networks, and the automatic tester will collect the result. And in either way, we want the automatic testers to output network problems, specific network problems. For example, there's a congestion between point A and point B.
Question. When you say testing, are you thinking of something that happens as part of the development phase or something that runs continuously in deployment?
In deployment. Yeah. So who will benefit from this kind of automated testing tools? Of course, network engineers, because now they can ensure the security compliance, such as PCI and HIPAA in the medical networks. And they can reduce the service downtime. And more importantly, when there's a problem, the network engineers will be able to report the specific errors to vendors instead of just a vague symptom description. So, but in addition, the network users also benefit from this kind of tools. The network users now have better visibility on the networks, of what's going on in their network. And automatic testers can reduce the application diagnosis time. For example, if there's an automatic tester says the network is okay, and the network users should focus on debugging their application because the network is okay. And in other way, if the automatic tester fails, then there's clearly a network problem. So the network users should engage the network engineers faster. So in this talk, I will explore 3 dimensions of the automated data plane testing. First, first dimension is called method. I've briefly described what method is previously. It basically means that whether we send out the test packets or not. If a tester does not send out a test packet, it's a static tester. It's not just testing without execution. If you think about the network as a program, you are testing the network without sending the test packets. And on the other hand, if the tester sends out the test packets, they are dynamic testers. They are testing with execution. The second dimension we explore is the knowledge, or how much we know about the data plane. So traditional network testing tools like ping and traceroute, they assume no knowledge about the data plane. So I call these tools black box testers. On the other extreme, the white box testers assume that they know everything about the data plane. Everything about the data plane is deterministic and static. So they know about it. And there's a gray box tester sits somewhere in between, assuming knowing something about the data plane. The third dimension I will explore is the coverage, or what kind of network components does an automatic tester cover? Do we cover links, rules, or queues? Is it even possible to achieve this 100% coverage? So in this talk, I will mainly describe 3 automatic testers during my PhD. And they explore different dimensions, different design points in this design space. First, I will describe ATPG, which is a dynamic white box tester that covers 100% of rules and links. ATPG is designed for enterprise network consisting of roughly 20 switches. And I will show the deployment result of ATPG on Stanford network. The second tool is called NetSonar. NetSonar is a dynamic gray box tester that covers 100% of links with probability. NetSonar is designed for backbone networks consisting of roughly 100 devices. And we have deployed and evaluated NetSonar on Microsoft's Interdata Center platform. And the third tool is called Libra. Libra is a static white box tester that covers 100% of rules. And Libra is designed for data center networks consisting of tens of thousands of switches. And I will show the result of Libra on Google's data center network. But this talk is really more about the system design. It's about how to apply rigorous methods to the data plane testing. We start from ATPG, which sets the foundation of with a rigorous model for data plan testing and coverage. And then Nesona enhances ATPG by handling the unknowns in the data plan with the gray box testing. And then finally, Libra takes an alternative method by simplifying the ATPG's model to achieve even larger scale in the data center network. So I will describe these three tools later. Yeah, let's start from ATPG, or automatic data test package generation. So in ATPG, we are trying to answer this question. Given all the forwarding rules and topology, how to use a minimum set of test packages to exercise 100% of the rules and links? The reason that we are interested about the coverage is we assume this fault model. A rule or link will treat all traversing packets identically, so that we only need one packet or one kind of package to exercise that link or rule to understand whether it's working or not. And the second assumption is a test packet traversing a faulty component should have some end-to-end effect, so that we can synthesize all the testing results and then pinpoint the faulty spot. So to test the network, first we need a model to abstract enough information about the data plan. I use the header space analysis for this abstraction. If you are not familiar with the header space analysis, basically you can think of it as a black box that takes in the data plan information such as forwarding rules and topology, and the pair of ports X and Y. And the outputs of header space analysis are all classes of packets that can flow from X to Y. By the way, a class of packets is just a set of packets that sharing the same header fields. For the original header space analysis only tells you the reachability analysis between one pair of ports. But we can push this method a step further. We can answer this all pairs reachability table. In other words, we want to calculate all classes of packets that can flow between every pair of ports. So what do I mean by that? Let's see an example. Suppose we have three routers, switch A, switch B, and switch C, and we have some rules in each of the switch. And we have three ports, PA, PP, and PC, where we can send in the test packets. Now, with the header space analysis or with this all pairs reachability calculation, we can generate an all pairs reachability table like this. This is a very important table. For each row of this table is a class of packets. It's one type of packets. For each class, we know its header, ingress port, egress port, and rule history. Rule history is what kind of tools that this class of packets will traverse throughout the network. And then if we send out all the packets in this all pairs reachability table, by definition, we can exercise all the rules. Because this all pairs reachability table contains all possible packets that can be delivered in this network. But if we look at this table more carefully, we can find something interesting here. The last packet, packet 6, all of its rule history have already been covered by other packets. That means even without packet 6, we can still cover all the rules. That means, so in this particular example, we save 1 out of 6 packets. But in real network, the saving can be significant. So we know that the packets in all pairs reachability table are more than necessary. We can select a minimum set of packets from this all pairs reachability table, whose packet history still cover the whole rules. So this turns out to be a min set cover problem. Why this is a min set cover problem? Let's look at the example here. Suppose we have this all pairs reachability table, and I will just show the rule history part of that table. Packet A exercise rule 1, packet B exercise rule 2, 5, and 6, etc. Right? If we see each row as a set, and our goal is to select some sets so that the union is R1 to R6, like packet B, C, and G here. So this is the min set cover problem. Unfortunately, the min set cover problem is NP hard. The optimization problem is NP hard. But fortunately, there is the polynomial time approximation algorithm. Because we don't really need the exact min set cover, we can afford to send out some more test packets. So the test packets in the original all pairs reachability table are divided into 2 parts by the min set cover. The result of min set cover becomes what I call them regular packets, and then the rest are the reserved packets. Regular packets if we send them out periodically, they can cover all the rules within the network and make sure the forwarding state is okay. For the rest of the packets, the reserve packets are simply redundant here, but they'll be useful for localization, which I will describe next. So for localization, so if all the regular packets have been delivered correctly, we know that everything is correct, perfect. But if there's something wrong with these regular packets, how do we pinpoint the faulty spot? To answer this question, let me just recall that the fault model we assume. In the fault model, we made two basic assumptions. One is a rule or link will treat all traversing packets identically. And secondly, we assume that a packet traversing a faulty component should have some end-to-end effect. If we accept these two assumptions, we can localize the fault by elimination. So this is the Stanford backbone, and let's look at an example. Suppose there's this red router, there's a rule in this red router, and instead of for the packets, begins to drop the packets. So how do we find that out? We send the first packet, it gets dropped. So we include all these packets' rule history into the suspect set. There's going to be something wrong with along this path. Right? We send out the second packet, it gets dropped again, so we include more links into the suspect set. We send out the third packet, now it passes. So we know that the rule history of this packet is okay, so we eliminate these three links from the suspect set. Basically, we repeat this process. And by sending out the first packets, we can already triangulate the problem to a specific router. By sending out more packets, we can even triangulate the problem to a specific rule or specific queue. So let's put everything we have discussed so far together. First, you have a network, and we want to collect all data plane information like topology and forwarding rules into the header space representation. Many operators have done this already, right? And this data plane information goes through the header space analysis, and we can calculate the all-pair switchability table I described before. On top of this regular all-pair switchability table, we can run the min-set cover algorithm to choose the regular test packets and deploy these test packets back to the network. And these test packets will exercise the network and will collect the testing result and do the fault localization if something goes wrong. So I have evaluated ATPG on two data sets. One is Stanford backbone, and the other one is Internet 2. Stanford University backbone has 10,000 forwarding rules and 16 Cisco routers, and Internet 2 have roughly 100,000 IPv4 forwarding rules and 9 Juniper routers. So for each data set, I calculate a number of regular packets needed to exercise all the rules. So the most surprising result here is that for Stanford network, we need only about 4,000 packets. And for Internet 2, we need about 35,000 packets. And remember, this number of packets are amortized across different ports. So the packets per port is even smaller. So if we assume 1 gigabit per second in Stanford or 10 gigabit per second in Internet 2, you can use less than 1% of the utilization, less than 1% of the overhead to test the network's entire network 10 times per second. In other words, you can find out the problem within 0.1 second. So why do we need so few test packets? There are two main reasons. First, the min-set cover algorithm reduced the number of test packets a lot. We've seen 160x reduction in Stanford network compared with the original all-pair switchability table. And we've seen 85x reduction in Internet 2. The second reason is that the rule set themselves is not random. They have structure in it. Routing protocols route the packets from end to end, and the access control rules are normally part of the network-wide policy. The result is that the same header will appear time and time again in different switches, so that our original all-pair switchability table won't grow exponentially in the first place. So I've shown that ATPG works in offline analysis. Does it work in the real world? So I've deployed ATPG on 3 Stanford buildings. There are more than 30 Ethernet switches. And we focus on the link cover rather than rule cover because the entire network is just a big layer 2 network. And we have 51 test agents. So now if you remember the original email I showed you in the beginning of this talk, this problem, like a loop problem causing by, I think, a spanning tree, this happens at the second day we deploy the system. So this was what was captured by the ATPG's link cover test suite. The x-axis is time and y-axis is the failures per minute. So you can see this this problem in the blue circle on the right is the problem in the email. It happens between 6 p.m. to 7 p.m. on October the 2nd. We've even seen a smaller unreported problem several hours before that. So this may be related. And in addition, we not only detect the problem, we triangulate the problem, and we go and ask the network engineers what happened, and we triangulate to the right spot in the network. So in summary, ATPG is a dynamic white box tester that covers 100% of links and rules. It is designed for enterprise networks, and I've shown the results of ATPG on Stanford network. ATPG is a rigorous method to describe the testing and coverage. It generates the test suite with all pairs reachability, and it minimizes the test suite with the mistake cover everything. And finally, it does this for localization by elimination. So I've shown that ATPG can generate a small set of test packages to cover all the rules. Will that work in a large network? So we've tried that in Microsoft's Interdata Center network and find several interesting things here. And the result is the new system called Nexonia. Let's see how that goes. So Nexonia is designed for a large network, and MSN is a very typical one. MSN is Microsoft's Interdata Center backbone networks that supports all Microsoft's online services, including Bing and Xbox Live. It connects tens of data centers around the world with more than 100 core routers. And the tunnel-based traffic engineering, or NPLS-TE, is used extensively in MSN. So our task is to scale ATPG to MSN with the test agents reside in the production machines in the data centers. So it didn't take long before we realized that the model for ATPG was greatly simplified. We assume the network is deterministic and step, and that's not true. There are so many unknowns in the data frame, in a true large data frame. First unknown comes from the non-determinism in the multipath routing. So remember that the MSN uses tunnel-based routing, where there are multiple tunnels setting up between two data centers. And these tunnels or paths may go through different links to balance the load. Right? For example, in this example, we have 6 routers, and there are 4 paths going from R1 to R4. Now, a hash function in R1 chooses which exact path to go to a particular packet will go to, based on the packet's header. Here, the header specifically means the IP source, the 5-tuple IP source address, IP destination address, TCP port, and protocol. The problem with this approach is that the hash function is considered proprietary. We don't really know what's in that hash function, because the chip designer just don't let us know. Let's suppose so what problem is that? So let's assume there's a packet drop problem between R2 to R3. If we use the old method in ATPG, we send out the test packets from R1 to R4. And there's no guarantee that these test packets will exercise this problematic link, R2 to R3. So if you can't exercise them, how do you know there's a problem in the first place? So the second unknown in the data plane is the routing changes. Traffic engineering recalculates the path every 15 minutes to adapt to the load, the changing traffic load. Well, that seems to be a long time. Actually, if you have a large number of tunnels, these updates can be very frequent. On the other hand, the forwarding table snapshot just cannot keep up with the changing speed. Why? Because the switch in today's, the CPU in today's network devices, switches and routers, are normally underpowered. And doing this snapshot frequently is CPU intensive. And network engineers just very reluctant to allow us to pull the information fast enough, of being afraid that doing so may affect the network's normal operation. I need to point out that there are actually 2 very distinct reasons for the data plane testing, for these unknowns in the data plane. The first reason is just bad engineering. For example, the hash functions are kept secret by the chip vendors for no good reason, and there's underpowered CPU in the switches and routers, also for no good reasons. And hopefully this will change in the near future. So I labeled them as temporary. But there's a more fundamental reason for the unknowns in the data plane. It's what I call the intrinsic nature of large data plane. For example, the changes in the network. If you have a large network, then inevitably you have a lot of things going on in your networks. So the result is that you have this inconsistent snapshot of your data plane, so that you don't know the exact state of your data plane. And another example is the hash function. Even you know what hash function is, there can be randomized algorithm in hash function, which is reasonable. That hash function just balance the load, right? So they probably will use a randomized algorithm. But the result is, again, you don't have the exact deterministic behavior of the network. So this, unlike bad engineering, which is temporary, these problems are lasting problems. They're unlikely to change in the future, at least not in the near future. And any practical systems should be able to handle that. So to solve this, to handle these unknowns in the data plane, I propose this gray box testing solution. And here I just describe two of the many gray box testing techniques I use in NetSona. The first one is called probabilistic path cover, and the second one is called traceable probes. So probabilistic path cover solves this problem, the hash function problem. For a class of packets, the switch has n paths to choose from based on the headers with an unknown hash function. How many different headers do we need to exercise all n paths? Of course, you need at least n headers. Otherwise, how can you cover all n paths? But in the worst case, you will have, no matter how many headers you use, you cannot cover them all, right? So here we need to make some reasonable assumptions. So I make these two assumptions. First, I assume that each header is hashed to a path with a uniform probability of 1 over n. And this is reasonable because it's hash function's job to balance the load as uniformly as possible. And the second assumption is that each header is treated by the hash function independently. In other words, the hash function is stateless. So if we accept that two assumptions, this turns out to be a very nice math problem, and the result is non-trivial. It's known as the coupon collector's problem. It states like this. Given a pool of n different coupons, from which coupons are being collected with replacement, what is the probability of collecting all n coupons in T trust? So here, obviously, coupons is equivalent to a path, and each job is sending out a random header to exercise the network. So the probability of you collect all n paths, collect all n coupons within K trust can be found in this formula, the first formula. The math behind this is really complex. But the more importantly, I want to remember that the expected value of T, the number of trusts needed, is in the order of n log n, where n is the number of paths. So that does increase a little bit faster than linear, but only modestly. Not too bad. So this is a figure showing how the number of headers you need to send out compared with the number of paths. The x-axis is the number of paths, n, and the y-axis is the number of tries you need normalized by n. So for example, this point means that to exercise a path, we need about 2.8 times of the headers, which are 2.8 times 8 is roughly 20 headers to exercise a path. This curve is the expected value, so this is only on average. But of course, the higher probability you want, 95%, 99%, the more headers you will need. But in general, these numbers all grow in the order of n log n. So now the second technique is called traceable probes. Traceable probes solve these two problems. The first problem is how to map these probes, the test packets, back to the links. Remember that the probabilistic path cover only tells you that the paths are covered, or how many packets do you need to cover all the paths. It doesn't tell you for each individual path, an individual probe, which packet can cover which packet can cover a particular path. In other words, we still don't know the path for an individual probe. The second problem is how to handle these path changes. Remember that traffic engineering just changing this routing information periodically. And as a result, the routing information captured by NetSonar can be outdated. So if this information is outdated, is incorrect, NetSonar may bring an incorrect link for the failures. And that's bad because that can cause the false positives. And we want to avoid these false positives caused by the path changes. So the solution to these two problems is use these traceable probes. A traceable probe is a pin plus trace route. A pin will measure the end-to-end latency between any 2 points, but the pin won't tell you the path information. But we can use the trace route to get the path information. Both the pin and trace route are TCP based. We use TCP trace pin and TCP trace route, so that they will reflect the application level experience. Both pin and trace route will use the exact same 5 tuple, IP source, IP destination, and UTC ports protocol, so that both pin and trace route will travel through the exact same path. And the number of the probes you need is just determined by the probabilistic path cover. The result is that now we can map each probe back to the path, and we can avoid these false positives caused by the routing changes, because now we have the path information in the probe. So again, let's put everything together. As usual, so NetSonar has 3 major components: controller, test agent, and data sync. The controller, as usual, just collect all the data plane information, paths and topology, and it does this probabilistic path cover, as well as mean-set cover. We study the mean-set cover because 2 paths may go through the same link, and there's redundancy here. And this, and then test agents just download the test plan generated by the controller and execute these test plans using the pin and trace route. And then the results are uploaded to the data sync for analysis eventually, also using HTTP. So we have deployed NetSonar on Microsoft's inter-data center network. So we deploy NetSonar to 8 Microsoft data centers, each with 10 machines, so that we can have 100 machine pairs between any two data centers. We cross-validate NetSonar congestion alerts against these router counters. So router counters, or in network terminology, is called SNMP counters. They are the counters that collect the statistics of each interface. For example, how many packets are forwarded, how many packets are dropped, etc. So they are mainstream monitoring method for today's network. So during February to March 2013, 55 out of 65 congestion instances, NetSonar instances, can be validated using these router counters. So for the rest of 10 instances, they are either false positives, NetSonar does something wrong, or they are not captured by the router counters at all. So, but due to the lack of these, ground truth, we don't really know which case it is. So some of you may ask, why don't we just keep using router counters if you use for validation? The reason is that compared with the router, setting a right threshold for the router counter is extremely difficult. So for example, compared with the router counters during April 2013, we have seen 3,000 high utilization or drops alerts in these router counters. And on this, at the same time period, NetSonar only sees 36 alerts, and 30 of them can be validated by these router counters. And how NetSonar works is that once it sees some application abnormalities, for example, the latency is too big, it will try to triangulate the problem. But so in other words, the rest of these router counters instance have no effect on the application level experience. So if you divide 3,000 by 36, that's an 80x reduction. So NetSonar helps network engineers to focus on the problems that actually matters to the application. So this is one instance captured by NetSonar, just an example. This figure is plotted by the router counters. We can see that at times equal to 16, the outgoing traffic just increases, and there's a lot of drops at the same time. Note that for NetSonNet to capture this particular interface out of thousands of interfaces in the network is non-trivial. NetSonNet has to design a test plan to cover all the bins. It has to synthesize a lot of pin and trace route results, and you need to disambiguate this multipath. So this is an incident. This is the interesting figure. This is called incident heat map in Microsoft's data center. So the x-axis is time, and y-axis is the machine pair index. And each dot here means that there's a latency problem. There's a latency problem. And we can see that there's for example, in this red circle, this is a widespread problem across multiple machine pairs. That means this is likely to be a network incident. However, on this in this circle, this instance only affects a small number of test agents, but that's for a long time. So they are likely to be the bad agents rather than the network problem, because they are just affecting a small number of test agents. And know that the test agents is deployed into the data centers using the production machines. So you don't really know what's going on in that machine. There may be some other process sharing the same CPU. So in this case, we need to eliminate the results from this test agent. And the third circle is very interesting. It's a symptom unique to data centers. So first of all, the incident affects a lot of machines, but they are separated by 12 hours. So they are not likely to be a random instance. They are coordinated. So they are likely to be the distributed applications running in the data centers. An example of distributed applications would be something like web indexing, where you have to fire a large number of machines simultaneously every 12 hours. So in summary, NetSonNet is a dynamic gray box tester that covers 100% of names with very high probability. NetSonNet is targeted for the background networks consisting of 100 devices, and it's deployed and evaluated on Microsoft's data center network, MSN. So what can we learn from NetSonNet? First, we learned that there are so many unknowns in the data frame, and they are from two distinct sources. One is from the bad engineering, and that may be temporary. And second comes from the intrinsic nature of large data frames, which every practical system should be able to handle. NetSonNet handles these unknowns with the gray box testing techniques. And here I describe two of them, the probabilistic path cover and traceable probes. So here now we have discussed the ATPG and NetSonNet. ATPG sets a foundation of the data plane testing and coverage, but we can't apply ATPG directly to large network because of these unknowns. NetSonNet will be able to handle these unknowns with the gray box testing. So in the rest of this talk, I will describe an alternative approach to scale ATPG through a system called Libra. Libra is a static tester for data center networks. It achieves ultimate scale with this simplification, the simplification to the ATPG's model. So there are two main simplifications for Libra. First, Libra now is a static tester rather than a dynamic tester. As a result, it cannot triangulate this performance problem, like link congestion problem, but it will be able to do the logical correctness checking by reading all the forwarding information. So again, recall that the static tester will not send out the test packets, but only reads the information from the data plane. So why do we care about the logical correctness? Because Libra is designed for data centers. And in the data centers, the protocol convergence, due to the size of the networks, is slow and less predictable. So it's crucial to make sure that your network is not stuck in a bad state. So that's where the Libra can help to verify the logical correctness of the network. And the second simplification comes from the rule. So in ATPG, we assume a rule is just a general match plus action tuple. In Libra, we focus on a very specific rule, the destination destination-based pure IP forwarding rules. So why do we care about this kind of rules? It's because it's what was used in the data centers. The forwarding scheme in the data centers it's pretty simple. It's just the pure IP forwarding, unlike what you will see in the enterprise networks or the backbone networks. So the benefit of these two simplifications is the scale we can achieve with Libra. So let's start from the static testing. Static testing the logical correctness without sending the test packets. The inputs of these static testers are destinations, which is the IP address. Normally, it's not a single IP address; it's an IP subnet. It's a collection of IP addresses. And rules, just forwarding rules, is termed the pure IP forwarding rules. And the topology is just how networks are connected together. The example failures of this logical correctness is loops, black holes, or partitions. Let's see an example here. So here we have A, B, C, D, 4 routers. And if everything is correct, all the packets destined to this destination IP2 will go from A to C to B. This is just one path. It can also go from A to D to B. I didn't show you here. Now, if something wrong happens, either there's a control logic bug or there's someone just typed in a bad command, this rule in the switch C, instead of forward the package to B, it forwards the package to A. So this is bad. Why? Because now it creates a loop. And because the package will go from A to C and from C back to A. A loop is bad in the network because, first of all, your packet never reaches its destination. It never reaches IP2. And secondly, the package will circulate between these two routers and consume the network resources. So that's where the Libra can help to detect these kind of problems. So before I describe the details of Libra, let's look at an important concept here called forwarding graph, which will be used extensively in Libra. A forwarding graph determines how the packet flows in the data centers, in a network. For example, again, for all the packets going to IP2, the packets will go from A to C and D, and from C and D to B. And since IP2 is a local address for B, B will just forward the packets. So this behavior can be abstracted using the forwarding graphs on the right, where each node is a switch, and each edge marks the forwarding direction of a packet. Now like here, not all the networks can be abstracted using a forwarding graph. We can abstract it using a forwarding graph because we focus on pure destination-based IP forwarding. So that each graph is simply a graph without any matching information. So there are many good properties of the forwarding graph. First of all, each destination has a forwarding graph, and they are mostly different. And secondly, all data plane abnormalities are just graph problems. For example, a loop in the network is just a loop in one of the forwarding graph, which is a strongly connected component. And black holes are just nodes with positive in degree but zero out degree. The third property is that the forwarding graph size is not too big. It equals to the physical network size. And this is because each physical node is a vertex. And finally, for each graph, only a subset of rules are needed to construct this forwarding graph. Because not all the rules are relevant to these destinations. If they are not intersected, why do we care about that for that rule? So if we have this abstraction of the forwarding graph, we can solve this general static testing problem using a divide and conquer method. So it comes in two phases. First, in the first phase, we will slice these networks. First of all, you have these networks with all the rules. We can slice these rules according to the destination. And for each slice, we can have a forwarding graph for that. For each destination, we can have a forwarding graph for that. And I call this phase a map phase, just slicing the networks into these forwarding graphs. And the second phase, I call it the reduce phase, is where you, in parallel, run this graph computation on all the forwarding graphs in parallel. So I call this phase a reduce phase. The reason I call these two phases map and reduce is because this algorithm can be implemented in a distributed computing system called MapReduce. So that's how Libra is built. So Libra, as usual, we download all the forward data plane information. Here, specifically the forwarding graphs, the forwarding rules into the distributed file system. And then in the second step, we just partition these rules into multiple small chunks of files called a rule shard. A rule shard just consisting sum of the rules. And then each mapper will take one rule shard and a full copy of all destinations. And its job is to output some intermediate results. Intermediate results is a key value result, where the key is the destination, and the value is the forwarding rule. Right? And the good thing about MapReduce is that mappers just need to output all these intermediate results, destination rule matches. And then MapReduce will shuffle all the intermediate results by their keys, which in this case is shuffling by destination, so that each reducer can get all the intermediate results sharing the same key, sharing the same destination. In this particular case, the intermediate results sharing the same destination are all relevant rules. The reducers can assemble the forwarding graph and do this graph computation in parallel. So here all the mappers and reducers are running in parallel, just like any MapReduce application. So we have evaluated Libra on three networks. One is the DCN, which is a Google emulated data center network. It consists of tens of thousands of switches, 2.5 million nodes, and over 10,000 destinations. And DCNG is 100 times DCN. It's 100 DCNs connected together using a star topology. And INET is an emulated ISP network consisting of 300 internet routers with full BGP table. Now, the key things here is that with tens to millions of switches, millions to hundreds of millions of rules, we can calculate the loop detection. We can do this loop detection on this scale of networks with just the minutes, within just minutes. For example, for DCN, with 50 machines, we can calculate the loop detection within that 1 minute. So, in summary, Libra is a static white box tester that covers 100% of rules. It is designed for data center networks consisting of tens of thousands of switches. And we have evaluated and deployed Libra on Google's data center network. The key of Libra is the simplification, and it does this simplification to scale. The two simplification described here is the static testing and pure IP forwarding. And Libra does this with this divide and conquer algorithm. Libra can do this static testing with the distributed algorithm in a distributed fashion. And Libra can be implemented on MapReduce. And for Google scale data center networks, Libra can check the loop detection within 1 minute. Okay, time to zoom out and conclude my presentation. In this talk, I'm going to describe how to apply rigorous methods to the data plane testing. We start from ATPG, which sets a foundation of automatic data plane testing and coverage. And then Nexona enhances ATPG by handling the unknowns in large data planes and with the graph testing tools, testing techniques. And then Libra takes an alternative approach. Instead of adding to the ATPG, it simplifies ATPG's model by using the static testing and the focus on the destination-based forwarding rules. So the result is that both Nexona and Libra can achieve higher scale. So in another perspective, the three systems described here explore different design spaces of their 3 dimensions: method, knowledge, and coverage. And all of them have been deployed to the production networks. But I need to mention that there's no one-size-fits-all solution for the network application. For example, using Libra for Stanford network is clearly an overkill because of the small size of the network. And we cannot apply ATPG to MSN directly because of the unknowns in the data frame. And with this, so we set out to help network engineers to win this battle against the various sources of network problems. And now, with the tools described in this talk, ATPG, Nexona, and Libra enhances humans' wisdom and intuition, reduce the service downtime, and ultimately save money. And our ultimate goal is hope is that network engineers no longer need to use their wisdom and intuition and rely on these tools so that they can put their efforts on more productive things. So these are some related works regarding these three systems described in this talk. I put the related works of ATPG and NetSonar together because they are both dynamic testers. Network tomography is the early effort to invert the data plane state while using these end-to-end measurements. But its goal is not to design a test plan. Its goal is to guess what's going on in the network that can best describe the observations collected. And on the testing design front, there's a NetQuest and robust monitoring, which use the Bayesian experimental design to the network. The main contribution of ATPG is its minimum test design with the mean set cover algorithm and its dual level coverage. And NetSonar further enhances ATPG with gray box testing. And NetSonar is the first reported large-scale data plane testers in the production networks. And similar to Libra, a lot of static testers have been discussed in the literature as well, but none of them describe how to scale to a very large networks like the ones in the data centers. The main contribution of Libra is speed and the scale of networks it can handle. And Libra is also the first reported static testers that is designed in a fully distributed fashion. So there are some limitations of future directions I think can bring this data plane testing a step further. We start from the complexity. Both NetSonar and Libra focus on scale. But some small scale networks is not easy to maintain either. For example, the enterprise networks is known to be very hard to maintain because of the constantly changing and relatively ad hoc policy requirements. And there are multiple packet transformations such as encapsulation, decapsulation, network address translation, etc., which makes this verifying these kind of networks very challenging. The second direction is what I call decentralized testing. So assume you have a very large network and it's hard to verify. And then you can divide these networks back into some smaller partitions. And you can verify these smaller partitions easily because of the scale. But then, so after you verify this intra-partition correctness, you may want to verify these, the correctness between the partitions. But that will require you clear definition of the correct behavior between the partitions, or the contract between the partitions. Which behavior is correct, which behavior is not. And finally, the device design. So far, we have assumed that we don't change anything about the network hardware. What if you can redesign the network? Redesign the network hardware? What kind of debugging facilities would you put into the network to facilitate this debugging? Here are some other contributions during my PhD. I contribute to NetFPGA, which is an open source hardware for networking research and education. I was one of the core developers for NetFPGA. And Jimlim, a cloud-based middlebox services with the help of software-defined networking. Acknowledgements. John, Dave, and Sachin, thanks for coming. Thanks for serving on my defense committee. I really enjoyed the discussion with you during different stages of my PhD, either on network verification or on other projects. I learned a lot from all of you, and I'm looking forward to the discussion in the next hour.
Or two or three.
Assuming, huh?
So, George, thank you. Many of the works described here wouldn't be possible without George. But I guess more importantly, George teaches me to stay curious and be bold. His knowledge across almost every aspect of computer science always brings fresh and exciting new ideas to our numerous discussions. And his optimism and enthusiasm helps me to overcome many difficulties during my research journey. So thank you, George. And my advisor, Nick, thank you. You teach me what research really means. He always encouraged me to be bold, to strive for perfection, and to think big. And during my PhD, I was very fortunate to witness this SDN movement, as the software-defined networking movement, evolved from a small lab project to a disruptive movement across the entire network industry. And I think that is the single most precious gift a PhD student could ask for, the determination to make real world impact. So thank you, Nick. And many of the work here wouldn't be possible without my collaborators. Peiben, Limo, Ming, Ratu, Lihua, Abin, Shidong, Fei, Mickey, and Junda. I was very grateful to meet and work with so many talented people. And thank you all. NetApp PGA team accompanied me through my initial years of my PhD. Thank you, Adam, John, Jonathan, Tatsuya, Grant, Jed, Andrew, Shabazz, David, Nikita, Paul, and Keith. Putting these open source tools in people's hands and seeing great projects coming out of it is truly amazing. And I want to thank the rest of the Macron group, past and present, Neda, David, Nikhil, Brandon, TY, Mahsa, and Rob, KK, Yanis. Thank you for helping me refine my publication and presentation, inspiring me with the new ideas, and leaving so much fun time in my memory. Thank you. And finally, I want to thank my families and friends, both locally at Stanford and remotely in China. My parents have always been supporting me unconditionally in every possible way. Even they are on the other side of the ocean and knew very little about the computer science. And lastly, Chuan, my wife Chuan, thank you for your encouragement. Your encouragement helped me to overcome many ups and downs in my PhD. And thank you for standing by me with endless doubt and being my strongest motivation to move forward. Thank you, Chuan. And finally, thank you all for coming today.
All right, so I think we'll start with general questions from the audience, and then as most of you know, then we'll go into a closed session with the committee for some additional questions.
So you mentioned a certain scale, right? Like the 20, 100, and tens of thousands. I'm wondering what the justification for this scale, or why you think that we can't do the higher scales maybe with some of the certain mechanisms?
So this scale is actually a byproduct of the types of the network. So this for a normal enterprise network, you just have 20 switches, and for data center networks, normally you will have hundreds of switches, and for data center networks, tens of thousands of switches. And this technique is more than just look at the scale, but actually look at the techniques used in these specific types of the network. For example, in the enterprise network, you will see a lot of NAT and encapsulation and access control rules, etc. Right? So your tool must be able to handle that. Whereas in the data center network, although the scale is huge, but the forwarding is very, very simple. So your tool should be able to handle that kind of scenario. So the short answer is not about the scale, it's about the types of the networks and the techniques used in those networks.
I have another question. You showed the heat map when you were trying to triangulate the problems.
Mm-hmm.
I'm wondering, like, looking at that picture, there could have been other boxes I would have drawn just kind of not knowing what you were doing. So how did you choose which of those boxes to draw?
I just look at that heat map and find something interesting. Especially that's something like it's separated by every 12 hours. That's a very interesting one.
Okay, very interesting.
And if you think about the data center networks, what are they really do with those data center networks? Those machines are not sitting idle. They are doing some productive things.
Mm-hmm.
So you will find out patterns. And that's actually very interesting. And actually, Netsona was built on top of this tool called internal to Microsoft called Pin Mesh, which is basically all pairs pin. And through that project, you can see a lot of patterns. So they even use a pattern recognition algorithm to analyze what's going on in the network. So definitely those heat map and these patterns are useful for this troubleshooting.
Sorry, I just have one last one.
We're gonna have to stay here until there's at least a couple more
This
questions.
is
So.
protocol independent, correct? Everything you've done is routing protocol independent, I believe.
Protocol-wise, yes, but for example, the Libra, for example, it focuses on this pure IP forward.
Mm-hmm.
Although it doesn't need to be IPv4, it can be IPv6, but if it's a prefix-based and destination-based forwarding, Libra can apply to that.
Yeah, good for
So it's generally protocol independent, but it requires some specific function or the style of the protocol.
Mm-hmm.
Another
So
go.
for
Oh.
right.
So in Libra, you're doing the MapReduce thing. What, in terms of scalability, what sort of limits the number of reducers you can have in the network? Is
Interesting
that
question.
just based on like, the number of IP destinations, or are there other limits than that?
Actually, there's no hard limit, but you will have some overhead with having so many machines. So in Google, what they do is they have a large server farm and you submit jobs to them. If you require, so you need to ask for the machines. If you ask too many machines, then this coordination will take some time. And in some cases, that will offset or even makes your having more machines useless because of this setup time. But theoretically, if the cluster is yours and this work deployment is instant, then you have no overhead.
So for ATPG, I wonder whether you consider access control policies and how that affect your test package generation.
Yes. In ATPG, we base ATPG on top of a model called header space analysis. And in header space analysis, both forwarding rules and access control rules are just rules. You will do some match plus action, right? As long as it's a match plus action rule, then you can abstract it out using ATPG, using the header space analysis. For example, the access control rules are just for this type of packets get dropped, right? Drop this type of packets. And when you do this all pair switchability, when you encounter this rule, you just stop the traversing of your packets and just stop there. So that will abstract these access control rules. And since ATPG is built on top of header space analysis, ATPG itself can handle this access control rules.
Any other questions? Going once? Going twice? Okay, thank you all for coming. Let's thank the wonderful. We'll take a 2-minute break and then go into closing.